With Unit 2. This video will be about learning Target 2C, which is about derivatives at points, higher order derivatives, tangent lines, and some table problems. So the majority of this video will talk about how I can take a derivative in general, but then evaluate it at a specific x value or a specific point that we're given. One thing that's super important to keep in mind is that we have to find a general derivative first. The reason being is if we try to plug in the number that we're given first, our function is just going to become a constant since we're plugging in a value for x, and the derivative of any constant is 0. So we cannot substitute in the value for x until we first find a general derivative. So that would represent the slope of the tangent line at any point. Then once we have our general derivative, we'll substitute in a specific point. A couple other things to review to keep in mind in terms of notation. Remember, a derivative has a couple notations that we can use, but y prime would be a first derivative, so would f prime of x if we instead had a function called f of x. Those both represent the first derivative. Also, we have that operator notation of dy over dx or df over dx also represent a derivative of y with respect to x or derivative of f with respect to x. All four of these notations are interchangeable depending on if you have a function that's y equals or f of x equals, and depending on if you're using the prime notation or the operator notation. Let's look at our first example. So in example 1, it says if f of x equals 7x minus 3 cubed, we want to find f prime of 2. So the first thing I have to find is I first have to find f prime of x in general. So I need my general derivative for this function. What rule or rules are we going to have to use to be able to take the derivative of 7x minus 3 all to the third power? Well, we're going to have to use the chain rule for sure, and then we'll also end up using a power rule in there when we take the derivative of this inside function here. So for our chain rule, our outside function here is the cube power. Our inside function is the 7x minus 3. So we'll start by taking the derivative of the outside. So the third power comes down. We would keep the inside the same. So the 7x minus 3 does not change. It is now raised to the second power since we took the derivative of that third exponent. So 3 comes down and we subtract 1 times the derivative of the inside, and the derivative of 7x minus 3 would just be 7. Now let's simplify this down a little bit so that we have combined anything we can. 3 and 7 are both scalars or coefficients that I can multiply together, and instead write this as 21 times 7x minus 3 to the second power. This right here is our f prime of x, or our general derivative for any x value. In particular, this problem is interested in finding f prime of 2. Well, now that I've found f prime of x, I can substitute in 2 into that function to find f prime of 2 specifically. When we do that, we'll get 21 times 7 times 2 minus 3, and all of that will be raised to the second power. Now, if this was a free response problem, we would not need to simplify our work, but if this was a multiple choice problem on an AP test, we would want to make sure our answer is matching, so we are going to go through and simplify it just for that sake. So we'll start by simplifying the inside. So I have 21 times, now 7 times 2 will give us 14, then 14 minus 3 will give us 11, so I end up with 21 times 11 squared. Remember, order of operations tells me that I have to do the exponent first before I do the multiplication, so I have to do 11 squared. 11 squared is 121, and then I have 21 times 121, which will give me 2,541. Now, of course, these numbers got very large compared to numbers that you would see on a multiple choice section on an AP test. So keep that in mind. Although we did not use a calculator here, you could always write out on the side 121 times 21 and do some good old-fashioned multiplication for that. Let's look at example 2. So example 2 says if f of x is the function x cubed minus 9x plus 1 times 2x squared minus 3x plus 11. And they want us to find f prime of 0. Well, before I can plug in x equals 0, I first have to find f prime of x in general. I always need to be figuring out what my derivative is in general, and I need to be stating that down on my paper so that I'm showing my work for how to find the derivative, and I'm explaining to the person that is grading my test that I understand how to find f prime of x in general. Well, to find the derivative here, what rule or rules are we going to have to use to be able to take the derivative of f of x in example 2? So here we're going to have to use a product rule, since I have this x cubed function times this quadratic function. So I'm using the product rule there. And then also we're always really going to have a power rule that we're dealing with, since we're going to have polynomials in this section. And then technically everything is also a chain rule, so we have a little bit of baby chain rules in there that are not making much of a difference, since the derivative of all these inside functions would be 1. So let's look at the product rule. Why don't you guys pause the video and use the product rule to take the derivative of f of x in example 2. Let's check that together. So the product rule says I take the derivative of the first term, or the first product. So the derivative of x cubed minus 9x plus 1 would be 3x squared minus 9. So that's the derivative of this first function, times, keep the second function the same, plus keep the first function the same, so the x cubed, I'm going to rewrite that entire thing, times the derivative of the second function, which would be 4x minus 3. So again, with the product rule, it is not the derivative of one times the derivative of the other. Instead, it is the derivative of the first term, keep the second term the same, plus keep the first function the same times the derivative of the second function. Now that we have our general f prime of x written down, or our general derivative written down, I can substitute in 0 for x and find f prime of 0, since they asked us for that value specifically. Now when I do that and I'm substituting in 0, a lot of things are going to 0 out. So I'll end up with this 3 times 0 squared minus 9. Then I'll have 2 times 0 squared minus 3 times 0 plus 11, plus I'll have 0 cubed minus 9 times 0 plus 1, and then on the last term we have 4 times 0 minus 3. That is really cumbersome with all those zeros in there. A lot of things are zeroing out, so this 0 squared times 3 is going to go away, and we'll just get negative 9 for the first term. Likewise, we'll just get an 11, and then we'll just get a 1, and then just a negative 3. So if I rewrite those out, I really have negative 9 times 11 plus a 1 times a negative 3. We fit it all in there. We can simplify this further by multiplying each pair out, so I get negative 99 minus 3, and we end up with negative 102 then. And that is equal to our f prime of 0. One thing I do want to point out is notice the difference here on what I've written. On each of these first lines in problems 1 and 2, I have f prime of x written because that is representing my general derivative. Now notice I had to write down this f prime of 2 or this f prime of 0. I didn't just put another equal sign, because if I didn't have this portion written with the f prime of 2 or the f prime of 0, if I just put an equal sign, you're telling me that when plugging in that number, that's still equal to the general derivative, which is not true. So this is one of those notational things that we have to be very careful on. Because I'm asked to find f prime of 2 and f prime of 0, I'm finding something, although it's related to my first derivative, it's not equal to the general first derivative. It's a specific first derivative at a given x value that they're asking for. So I have to make sure I'm writing down that f prime of 0 and f prime of 2. And we talked about that a lot when we did continuity, and we were finding that f of that function value, that we want to make sure our notation is correct there. Okay, let's look at example 3. Here they gave us the function f of x equals negative 2x times 3x minus 1. That whole term is squared, and they asked us to find f prime of 1. We have to find a general first derivative first. So I have to find an f prime of x in general before I can find an f prime of 1 specifically. What rule or rules will we have to use to take the derivative in example 3? So in example 3, we're going to use a product rule. Since I have 2x, or negative 2x, times this 3x minus 1 squared, we are also going to use a chain rule. Because of the 3x minus 1 squared, the derivative of that will involve a chain rule. And then, since these are polynomials, we do have those power rules and derivative of constants in there as well. Why don't you guys pause the video and find your derivative on example 3. Okay, let's check our derivative. So the product rule tells me I take the derivative of the first. So the derivative of the negative 2x would just be negative 2. Keep the second function the same. Plus, technically, the first function, which would be a negative 2x. So if you wanted to, you could just write minus 2x instead of plus and negative 2x. Times the derivative of the second function will be our chain rule. So our outside function here is the second power. So that second power comes down. We will keep the inside the same, and that will all be raised to the first power. So the inside of the 3x minus 1 gets rewritten since that stays the same, times the derivative of the inside will just give us a 3. Now this is pretty cumbersome. I'm going to combine a little bit of things that I can. So I'm still finding f prime of x in general. So I'm just going to write an equal sign since it's equal to the prior line. I have a negative 2 times 3x minus 1 squared. And then over here on the second term, I have a negative 2 times a 2 times a 3. So all of these are coefficients on there. That's going to end up with a negative 12. And then I have that x and then that 3x minus 1. Now, of course, you don't have to do this step of cleaning it up, but I just think it looks a lot nicer before we go to find f prime of 1 in general, or specifically now. So now that we have our f prime of x, I can find f prime of 1 by substituting in 1. So I'll get negative 2 times, well, 3 times 1 is just 3, minus 1 squared, and then I'll get negative 12 times 1. And then again, 3 times 1 is still just 3, so I get that 3 minus 1. Simplifying this down, we have a negative 2. 3 minus 1 will give us a 2 squared. We end up with a negative 12 times a 2. Condensing all of that, order of operations says I do the exponent before the multiplication. So 2 squared is 4. So I end up with negative 8 minus 24 then. So we end up with a negative 32. That's our final answer. And again, if this was a free response problem, we would not need to simplify it down all the way. In fact, we could actually leave our answers once I have that line where I've substituted stuff in. So I'll highlight them in green for us. If we have a free response, I could actually just leave my answer on this first problem with this first line once I have that x value of 2 plugged in. Same thing with 2. If I did not have to simplify, if it was a free response, I could leave my answer here where I plugged in all the zeros. And on this last third example here, I could leave my answer unsimplified from this first step of just plugging in the 1 for x. But I did want us to just practice simplifying things because these problems do tend to show up on the multiple choice, so we want to get in the habit of simplifying for a multiple choice section since we have to have the answer match. So those were our first 3 examples where we were given a function, asked to find a derivative at a specific x value. And just to recap, to do that, we have to first find a general derivative first. So on all of these, we found an f prime of x first, our general derivative, before we specifically found the f prime of 2 value, the f prime of 0, or the f prime of 1. Let's look at some other problems that are actually related, even though we've got limits now. These are related to derivatives. So back in Learning Target 2A, we learned that the definition of the derivative goes back to a limit. And so what these limits are here for is we want to connect those back to our definition of the derivative. Now we have 2 definitions of the derivative. We had that regular form, which was the limit as h approaches 0 of f of a plus h minus f of a all over h. Then we also had the alternative definition, which I can write on the side for us, since both of these problems will deal with the alternative one, which says that f prime of a equals the limit as x approaches a of f of x minus f of a all over x minus a. So that was our alternative definition of the derivative there. And what both of these are asking us is we want to identify these limits as derivatives, and instead of actually taking the limit and doing algebraic manipulation on all of that, we can instead think about it as a function and figure out, well, if I know what my f of x is, and I know what my a is, and I know that this limit is equal to f prime of a, well, instead of finding the limit, I can just find f prime of a, which will be a lot quicker than trying to manipulate a limit around. So let's look at the first example. It says evaluate the limit if it exists. We have the limit here as x approaches pi of x to the 30th minus 8x minus the quantity pi to the 30th minus 8 pi all over x minus pi. This is representing a definition of the derivative. If I try to direct sub in, I would end up with 0 over 0, which is an indeterminate form, and we would have to go through some type of algebraic manipulation to be able to take the limit. But instead, I want us to focus on the definition of the derivative. So this is representing a derivative at a point. Oop. There we go. And so instead of thinking about it as a limit, let's identify what function are they taking the limit of here, and what a value do we have? What do you guys think? What do you think is our f of x value, and what do you think is our a value? Keeping in mind the alternative definition that we have written down over here in red. So for this example, our f of x is going to be this x to the 30th minus 8x, this whole first part of that numerator. Since in our alternative definition of a derivative, I have f of x minus f of a. Now the a value is going to be pi, since that's what x is approaching, so x approaches a. I also have that pi there. I can also check and make sure that the second term in the numerator should be f of a, which would be f of pi in this case, and that is equal to that. So what this allows us to do here is this limit then is going to be equal to f prime of pi, where f of x is this x to the 30th minus 8x. So instead of finding the limit and going through algebraic manipulation, if I know that this limit is equal to f prime of pi, well, let's just find f prime of pi then. That would be an easier route to take. To find f prime of pi, I need to first find a general derivative, which is why these questions are in this section. So first find your general derivative. What would f prime of x be for this function f of x? So for this function, we'd use the power rule, and I'd get 30x to the 29th minus 8 would be my f prime of x. Then to find f prime of pi, since pi is my a value, I can sub in pi in place of the x, and I'll get 30 times pi to the 29th minus 8. Now there's nothing that I can simplify down more than that. Since pi is an irrational number, I can't combine any like terms here. So there is our final answer. And I'm going to go ahead and highlight it because it's going to get a little cumbersome to box. But our f prime of pi is equal to this limit, since this limit is really representing the definition of the derivative for f of x at x equals pi. So our final answer there is the 30 times pi to the 29th minus 8. And if we were to take the longer route of trying to algebraically manipulate this limit, we would get that same answer. But as we can see here, this is quite a bit quicker since I only had to apply the power rule to take a derivative and then plug in that x value, or that a value that was given. Okay, example 5 is similar, but instead of having us find what the limit exists, it just wants us to explain what the limit statement represents. So it wants that explanation of it is a derivative at a point, but we need to figure out what our function is and what our a value is. So this is going to be a derivative at a point. It is also using the alternative definition. Since I have that as x approaches a number, I have what looks like could be my f of x minus f of a over x minus a. And we're trying to talk about what this represents. So this limit is going to equal f prime of something, where f of x is some function. So let's figure this out. What is our f of x function for this guy? What do you guys think? Well, for this example, our f of x function is going to be that natural log of x plus 1. So that right there will be our f of x function, since that's the first part in our numerator, and the alternative definition has that f of x coming first. What do you guys think our a value is? So in this case, our a value is going to be 1. A couple places we can see that as x approaches a. So x is approaching 1, so a has to be 1, or we have that x minus 1. So what this limit represents is this is representing, oops, come on, there we go. Oh, it's not, sorry, see if it wants to connect to the screen again. There we go. So this is representing f prime of 1, I'm just going to write pi from the prior example, f prime of 1, where f of x is equal to that natural log of x plus 1. So this limit is really equal to f prime of 1, where f of x is equal to this natural log of x plus 1. So that's what this function is, or this limit statement is representing. And that would be our answer there. And the reason it's f prime of 1 is because our a value here is 1. Okay, let's look at our next page. So our next page is going to deal with some higher order derivatives. So far all we've talked about are first derivatives. But if a function is more differentiable, or if the first derivative is differentiable, we actually have higher order derivatives here. Let's look at some of the notations for those. So on this first one here, we have the derivative. They're saying which is y prime or dy over dx. We call that the first derivative. And that's what we've been working on so far. So this is the first derivative of y. Oops, there we go. With respect to, so remember WRT is with respect to x. That was talked about, I believe, in our last video. So y prime or dy over dx is called the first derivative of y with respect to x. If the derivative is differentiable, so if y prime can have a derivative taken, then we can continue to take derivatives. And this process will continue as long as that next derivative is still differentiable. So our next derivative, we would note that with y double prime, since I'm taking a prime of something that already has a prime, or this d to the second y over dx squared. Now, I'm never going to pronounce it like that again. This is the second derivative of y with respect to x. Or we can use the prime notation and use y double prime. So this is the second derivative. Whoa. Sorry, I'm having pen issues. So this is the second derivative. Come on, there we go. Of y with respect to x. So y double prime, or our second derivative of y with respect to x. And the reason the 2 is on the d on top is because it's the second derivative, but both times it's taken with respect to x, so that's why the square is on the x in the denominator. We can continue this process. You can probably guess that if I have y triple prime, that is going to give me the third derivative of y with respect to x. Come on. And this can continue on forever and ever, but the prime notation does start to get messy. If I have 4 primes that I have to write, even if I have 3 primes, it looks very cumbersome. So this is one of those benefits of having multiple notations, is as you're starting to take higher order derivatives, that operator notation that we had of dy over dx, or the second derivative of y with respect to x, that's a lot cleaner to look at than y with so many primes next to it. Another alternative for that is once you get to the fourth derivative, instead of writing y with 4 primes, we would instead write y to the, and we would have a 4 in parentheses. Now those parentheses are needed around that number, otherwise I wouldn't know the difference between y to the 4th and the 4th derivative of y. So we have those parentheses around there to explain and to kind of make it so that we have a derivative, not a power there. So in general, if I have y to n primes, or the nth derivative here of y, this would be the nth derivative of y with respect to x. So this process can continue on for however many derivatives we may need to find, or however many derivatives they're asking us for. Let's look at our first couple examples for these. In problem 6, it says find the first 4 derivatives of y equals x cubed minus 5x squared plus 2. Now, for me to find the second derivative, the only way I can do that is if I first find the first derivative. Likewise, the only way I can find a third derivative is if I first have a second derivative, but then I need a first derivative to begin with. So even if the question asks me to find the fourth derivative, I have to find all the ones prior, and that work needs to be shown. So in question 6, they're asking for the first 4 anyway, so I need to have all of those listed, but even if it just said find the fourth derivative, I would still have to list the first, second, and third derivatives as well. So on each one of these, I'm going to use both notations. So y prime is equal to dy over dx. So we have both of those there, and let's find our first derivative here. Our function is a cubic, so I just have a power rule here. So our first derivative will be 3x squared minus 10x, since the plus 2 is a constant and will drop out. Now I can find y double prime, or the second derivative of y with respect to x. And the way I can do that is to use the power rule on the first derivative. So y double prime, I need y prime because I'm just going to take the derivative of y prime from here. So our y prime is 3x squared minus 10x. So the derivative of that would be 6x minus 10 then. And this process is going to continue. If I'm going to find y triple prime, or the third derivative of y with respect to x, what I'm looking at is the second derivative and taking its derivative. So the derivative of 6x minus 10 is going to just be equal to 6, since the 10 is now a constant and drops out. And then since they asked us to find the first 4, our fourth derivative there, remember, not going to use all those primes, but I have that 4 with parentheses around it to mean derivative, or the fourth derivative of y with respect to x. Since our third derivative here is just a constant, then the derivative of that is just going to be 0. So there are our first 4 derivatives for that function in example 6. Now let's look at example 7. It says find the second derivative of f of x if f of x equals 4 minus 2x to the 7th. So to find the second derivative, I first need the first derivative. Now we're using f of x here, so I'm going to call this f prime of x then for our first derivative. What would I have to use to find the derivative there of f of x? I'm going to have to use a chain rule. So I have an outside function here, which is the 7th power. Then I have an inside function, which is that 4 minus 2x. So the 7 power comes down. That will then be to the 6. Keep the inside the same. So 4 minus 2x does not change, times the derivative of the inside here would be a negative 2. So using the chain rule, we're able to find f prime of x. Now I can go and find f double prime right away, but I'm going to clean this up a little bit. And this is going to be true as our derivatives get a little bit more complicated. So in example 6, when I took y prime, there wasn't anything I could have combined there, but if I could have combined some like terms, I would have wanted to do that. And in example 7 here, the 7 and the negative 2 are both a scalar, so I'm going to go ahead and just multiply those to begin with and have them together as one term in front. So our first derivative is equal to negative 14 times 4 minus 2x all to the 6. Now they asked us to find our second derivative, so I have to take one more derivative. That would be equal to f double prime, since that's meaning the second derivative. And again, I'm going to have to use a chain rule. So the negative 14 is a coefficient, it goes along for the ride, but the 6 here is our outside power, so the 6 comes down. Oops, let me erase that little mark. I then keep the inside the same, so 4 minus 2x does not change. It is now raised to the 5th power though, since I took the derivative of the 6th power. So the 6 came down, so now to the 5th, keep the inside the same, times the derivative of the inside there is going to be another negative 2. And from here, I'm not going to bother to simplify it. If we wanted to, we would multiply the negative 14, the 6, and the negative 2 together all in front, but I'm going to leave my answer unsimplified. And they just asked for the second derivative, so that is truly my final answer. But I have to have f prime of x on my page's work because the only way to get to a second derivative is to first have a first derivative and then differentiate that function. Now let's look at one more example on this page. So this example is going to combine kind of the two main things we've talked about. We have a function. They're saying f of x is equal to 16 times the square root of x, and they want us to find f double prime at 4. So we're finding a second derivative, but then they want us to evaluate that at x equals 4. So we're going to combine these first two concepts in this video. One thing I want to think about right away is the square root isn't easy to look at. Instead, I can rewrite this as 16 times x to the 1/2 so that I can think about taking it as a power rule. And I always recommend that anytime that you have a radical there, rewrite that as the fractional exponent. Why don't you guys pause the video and find f prime of x, and then find f double prime of x in general, and let's check those two together. So let's check f prime together. So to take the derivative here, I'm just using the power rule. So the 1/2 comes down, 16 times 1/2 is going to give us 8, and then I end up with x to the negative 1/2 there. To find f double prime, I'm going to take the derivative of f prime. So the negative 1/2 comes down. 8 times negative 1/2 would give me a negative 4, and then I'll have x to now the negative 3/2. So we have our f prime and our f double prime in general. Those I needed because eventually I want to find f double prime of 4, but the only way I can do that is by having an f double prime in general, which means I also need an f prime in general. So now to find f double prime of 4, we're going to substitute in 4 for x. I end up with negative 4 times 4 to the negative 3/2 power. Now, if this is a free response problem, you are more than welcome to leave your answer here. And in fact, on a free response problem, please do not simplify your answer once you get a numeric answer, meaning I have no more x's. I just have numbers in there that are multiplied, divided, added, subtracted, raised to powers. I just have numbers in there. But in case this is on a multiple choice, we need to know how to simplify this. So we're going to take a little algebra review mini session here. So when I have a negative exponent, I can rewrite this as a positive exponent by flipping it down to the denominator, and I'll end up with the negative 4 in front, though still stays in the numerator since that is not raised to the negative 3/2. Just the 4 comes down to the denominator. The next thing I have to worry about is what is this 3/2 power? Well, if I have 3/2 as a power, I have two things going on here. 2 is my index. It is representing that square root. Remember, if I look back over here, the square root became the 1/2 power, so that 2 is representing that square root then, and 3 is going to be the power in there. So I can rewrite this then as negative 4 over the square root of 4 all to the 3rd power. Now that's definitely nicer to look at. I can simplify it down. The square root of 4 is 2. So I end up with negative 4 over 2 to still the 3rd power. Then 2 to the 3rd is going to be 8. And negative 4 over 8 will give us negative 1/2. So again, if it is a free response problem, please don't simplify your answer. And in fact, please leave your final answer unsimplified. But a lot of the times these are on the multiple choice section. And in that case, we would need to know how to simplify it down all the way down to the negative 1/2. Okay. Let's move on to tangent lines. So another kind of, it's not really an application, but another kind of extension to derivatives that we can take is we've done derivatives at points, we've done higher order derivatives, but we can also write equations of tangent lines, which shouldn't be too surprising since the definition of a derivative graphically is the slope of the tangent line at a certain point. So in the next couple examples, we're just going to practice writing those equations for those tangent lines. To make your life easier, please use point-slope form. Now, it does not matter what form of an equation of a line you write it in. Point-slope form and slope-intercept both represent equations of lines, but for the sake in calculus, point-slope form is easier because we're not always given a y-intercept. And why would we want to spend more time finding a y-intercept if I have a point and I have a slope right off the bat? So let's look at this first example. We want to find the equation of the tangent line to f of x, which equals 7x squared minus 13x plus 1 at x equals negative 1. Well, I have point-slope form over here, and I want us to look at it just as a little algebra review. So point-slope form tells us y minus y1 equals m times x minus x1. And in this case, x1 comma y1 is our point that we have for our equation, and m is equal to our slope. Now, because we're in calculus, we're not going to be finding slope using 2 points and using the slope formula. Instead, our slope is our derivative at a point. So the slope is equal to a derivative at a point that we are given. Okay? So that m is really going to be our f prime of a, where a is going to be that x value of that point that we are given. So let's look at our first example here. We have the tangent line of this quadratic at x equals -1. Well, so far they gave us a function. I can take the derivative of that function. That will give me a derivative in general. And then we can plug in x equals -1 to get the derivative specifically at -1. So let's start there. Let's find f prime of x in general first. Why don't you guys pause the video and find f prime of x. So f prime of x here will be 14x minus 13 using the power rule. From here I can find f prime of 1 since that's the, or -1, since that's the x value that they gave us. Substituting that in, I get 14 times -1 minus 13, which will simplify down to be -27. Actually, I'm going to write it underneath in case I need some space over there. So this will be equal to -27 then. So what information have we found so far in terms of point slope form? Well, right now we found our slope. This f prime of -1 is equal to our slope. That's our m value that we have. Now, I also have my x1. They gave it to me, x equals -1, but I don't have a y1 given. How can I find my y1 value? Well, I could find my y1 value by substituting -1 into the original function. So y1 will be equal to f of -1, since the way I get a y value is by plugging an x value into that function. When I do that, I end up with 7 times a -1 squared minus 13 times -1 plus 1. So overall then I have a 7 plus 13 plus 1, so I end up with 21 then. What that tells me is that my point that I have is going to be equal to -1, 21. So I have a slope by finding a derivative and then substituting in the x value they gave us. So our slope here is -27. I have a point. Since I had an x value, I can use that x value, sub it into the original function to get the y value. And now using that information, let's put it into point slope form, and I'll get y minus 21, since 21 is my y1, equals my slope, which is -27. I'll put the negative sign in there, times x minus a -1, or just x plus 1, because I'm going to simplify that down right away. And that would be our equation for our tangent line for this function f of x at x equals -1. Okay, let's look at example 10. So it says to find the equation of the tangent line to f of x, which equals 4 over x minus 2 at x equals 4. So I'm going to make a suggestion here that we have two options for taking the derivative. We could leave this as a quotient rule, and if we leave it as a fraction, we'd have to use the quotient rule, or I can rewrite f of x here, and I'm going to rewrite it as 4 times x minus 2 to the negative, first power. Sorry, that ran into the box. So I can move that x minus 2 up to the numerator, but it makes that exponent, which it does have an invisible 1 as an exponent there, into a negative. So 4 times x minus 2 to the negative first. Using that, why don't you guys find f prime of x in general, and then find f prime of 4, and we'll check that together. So f prime of x in general will involve a chain rule. I bring my outside function here is a -1. The inside function is x minus 2. The 4 is just a coefficient, so it's going to go along for the ride. Take the derivative of the outside first, so the -1 comes down, and I'll end up with a -4 then. All of that will be to the -2. I'm going to keep the inside the same, which is the x minus 2, times the derivative of the inside there would just be 1. And of course, multiplying by 1 is not going to change that derivative. I can now substitute in 4 for x, and I'll get negative 4 times 4 minus 2 to the negative second. Because I do want to simplify this down since I'm plugging it in for my slope, I could rewrite that as negative 4 over, simplifying the 4 minus 2 will give me a 2, and then moving that exponent down will make that positive. So I'll get negative 4 over 4, and I'll end up with, whoops, a negative 1. That was supposed to be an equal sign. So again, moving that exponent down to the denominator makes it a positive 2, and I also simplified the 4 minus 2 at the same time, which is why I now have a 2 in my base. 2 squared gives us 4, negative 4 over 4 is going to give us that negative 1. This, remember, is representing our slope. That is our m value for our tangent line. I have my slope, I have an x value, but I need a y value. How will we find the y value? To find the y value, we're going to have to plug that 4 into the original function. We could use either of these. Because I want to simplify it, I'm going to actually use the original one, the original f of x that was given, just so that I don't have to remanipulate stuff. So I end up with 4 over 4 minus 2, which is 4 over 2, which will be equal to 2 then. So this tells me that I have a point at 4, comma 2. Now we can put that all together with our equation of our tangent line. Why don't you guys pause the video and write out your tangent line, and then we'll check it together. Using our point slope form, I'll get y minus y1, which is the 2, equals our slope, which is just a negative 1, times x minus the 4, since that's our x1 value. And that will be our equation for our tangent line on example 10. Okay. To look at example 11. So example 11 here says find the equation for the tangent line to the curve y equals x squared plus 3 all over 2x at x equals negative 1. So again, I have a rational function here as my original function. Before in example 10, the reason I wanted to rewrite it was the numerator was just a constant. So instead of doing a quotient rule, a chain rule here would be a lot easier. But down here on example 11, I could rewrite this and I'd have x squared plus 3 times the entire 2x to the negative first. But because the numerator here is not a constant, I would actually have to do a product rule and a chain rule. So I think it would be easier to just leave it alone and just use a quotient rule then on example 11. So why don't you guys find y prime using the quotient rule for example 11. Okay, our derivative here for the quotient rule, I get the bottom function, so the 2x times the derivative of the top, which would be also a 2x, minus the top function, so the x squared plus 3 times the derivative of the bottom, which would be 2, all over the bottom function squared. So the entire 2x is squared there. I could simplify and combine like terms down if I wanted to, but I'm about to just plug in x equals 1 in place, so there's really no need to simplify in general first and then simplify again. So here we're going to find y prime evaluated at x equals 1. So this notation can be used in place of that f prime of like 4 that we used in example 10. When I have a y, I don't usually write y of x, so instead we could use this vertical bar, which would mean evaluated at the x value that's given, which is x equals 1. So this is similar notation as the same thing as finding like f prime of 1. To do that, I'm plugging in 1 for x. I'm not going to write out times 1. It's going to look very cumbersome, so I'll have a 2 times a 2 minus, I'll get 1 plus 3, which is 4, times another 2, all over 2 to the second power. If we simplify this down on top, we get 4 minus 8 over 4, so we end up with negative 4 over 4 again. So we actually get the same slope as we did in example 11. Remember, this y prime evaluated at x equals 1 is giving us our slope value. I have a slope, I have an x value, we need a y value, so I'm going to find y evaluated at x equals 1. I would not want to really write y equals because y equals is this x squared plus 3 over 2x. So I'm specifically finding y at x equals 1. By doing this, I can sub in 1, get 1 plus 3 over 2 times 1, 4 over 2 gives us 2. So our point here then is going to be at 1, 2. We can write the equation of the tangent line using point slope form. So y minus 2 equals our slope, which is -1 times x minus 1. That would be our final answer then for example 11. So we can see how we're putting together a lot of concepts from this section. Derivatives at points, which is what we started this video with, can be expanded to a lot of other concepts, tangent lines, or higher order derivatives as well. So let's look at our next example. Example 12 here says, suppose f of 2 equals 3 and f prime of 2 equals -1/2. We want to find an equation of the tangent line to f at x equals 2. Well, this is definitely different than the prior three examples. I don't actually know what f of x equals. Nowhere on here have they told me f of x equals some function. Instead, they gave me two pieces of information. They told me f of 2 equals 3. They also told me that f prime of 2 equals -1/2. And I want a tangent line at x equals 2. So if I start to set up point slope form, y minus, well, I don't have a y1 value, equals, I need a slope, but I know that this is at 2, so I'll have x minus 2. I really do secretly have this information. It's just given to me in another way. Let's look at the first piece that they gave us. F of 2 equals 3 is saying that when I plug in 2 for f, or 2 for x into f of x, I get 3 out. Well, that's corresponding to the coordinate pair 2, 3, which means that our y1 value is going to be equal to 3 then. Now the second piece of information is the derivative of f at x equals 2. This is our slope. This is our specific derivative at that x value, which they're asking for at x equals 2, which tells me -1/2 is my slope. So I can sub in -1/2, and I have my tangent line. So in this case, although it looked maybe like I didn't have enough information, this was actually a lot easier to do because there wasn't a derivative to compute. I didn't have to find the f prime of 2. It was already given to me. I just have to know how to move those moving pieces around. Okay, last example on this page is example 13. So this is really going to build on some of these concepts and pull in some stuff from algebra as well. So 13 says the function g of x is defined by g of x equals x squared plus b times x, where b is a constant, if the line tangent to the graph of g at x equals -1 is parallel to the line that contains the points -1, -3, and 3, 5, what is the value of b? That's a loaded question. So let's take this piece by piece. We have a function. I'm going to highlight things instead. They gave us what g of x equals. We know that b is a constant, and eventually our goal is to know what does b equal. They're also telling me that the line tangent to the graph of g at x equals 1, so that's a long-winded way to say the tangent line of g at x equals -1 is parallel, keyword, to the line that contains these 2 points, -1, -3, and 3, 5. Well, what's true if something's parallel, if two lines are parallel? Let's start there. Two lines are parallel, they have the same slope. Okay, well, I'm going to start with the actual values we have. I've got 2 points. I know from algebra that I can find the slope between 2 points. So a little review, that would be y2 minus y1 over x2 minus x1. So let's find the slope between those 2 points. So I'll have 5 minus a -3, which would be plus 3, over 3 minus a -1, which would be 3 plus 1. So I end up with 8 over 4. So I get a slope of 2. Now that's the slope between those 2 points. But because that is this line is parallel to this other tangent line, that means the slope of my tangent line also has to be equal to 2. Well, let's find the slope of the tangent line in general. So to find the slope of this tangent line, I would want to find g prime of x. So the derivative of this g of x would be 2x plus b. Since remember b is a constant, so it's just a number. So if I have a number times x, I'll just get that number left over. So that's a general derivative, but we're specifically talking about at x equals -1. So our slope then for this tangent line is really what g prime of -1 is, which would be -2 plus b if I substitute in a -1 for x. Because these lines are parallel, it tells me that the two slopes I found, both of these are m values, they're both slopes, they have to be equal. So what I have here is a system, or not a system of equations, but I have an equation that I can set up and solve for b. So I found this first slope of the 2 points by using the slope formula from Algebra 1. Then independently, I found the derivative of g, and I plugged in -1 since I'm taking a tangent line at -1. That gave me this slope of -2 plus b. Because they told me the tangent line is parallel to the line that goes through those 2 points, it means the slope from that line, which was 2, has to equal my g prime of -1, which is my slope of my tangent line. So I have that 2 equals -2 plus b. So from here, I can solve for b by adding 2 to the other side, and b would have to be equal to 4 then. So this example 13 really took a concept and expanded it out. There's a lot going on here with the moving pieces, but if we take it one part at a time, start to piece together what each piece tells us, then we can slowly put together all the pieces of this puzzle. The other thing I suggest on problems like these is I would focus in on numbers that you have to start with. So the reason I started by finding the slope first is I have 2 points, I know how to find the slope between those. So let me use that information and get at least that part of this down. Even if I'm not exactly sure where the problem's going to lead me, the more I can write down that I know is true and I can compute to begin with, the better chance I have of getting to my final answer there. And it's also work that I'm showing on my paper, and any work I have on my paper is going to be better than just leaving the problem blank completely. Okay, let's look at this little bonus type of question. So on 14, it says let y equal u times v, where that is the product of the functions u and v. We want to find y prime of 2 if u of 2 equals 3, u prime of 2 equals -4, v of 2 equals 1, and v prime of 2 equals 2. Well, to do this, I ultimately need to find a y prime to start with. Since I have a product of 2 functions, I'm going to use the product rule. Now, I don't know what u and v are equal to, but I know how I can represent their derivatives. I'm going to start by taking the derivative of u, which I'm just going to call u prime, times keep v the same, plus keep u the same, times the derivative of v, which would be v prime. Now I still don't know what u and v are equal to, but I know that if I have a prime on there, it's representing the derivative. They're asking me to find y prime of 2. So let's plug 2 in. I'll get u prime of 2 times v of 2. Plus u of 2, not minus, times v prime of 2. Now from here, I actually have all these pieces of information. I just got to sub them in where they belong. So u prime of 2 is equal to -4, v of 2 is equal to 1, u of 2 is 3, and v prime of 2 is 2. And I don't need to simplify this down. If I do, I'd get -4 plus 6, so I'd end up with a +2, but it would be fair game to leave it at this first answer once I have numeric values. Now I could not leave this at this first part since these are not numerical values yet. So this is kind of just how can we extend these concepts to using the product rule, quotient rule, or chain rule in general. And in the last video, I did say that as we continue on, and this is really the first example we're seeing, we're not going to have all of our functions defined for us, but we still have to be able to apply the product rule, quotient rule, and chain rule. Let's look at it in a little bit of different format. So examples 15 through 18 here are similar to 14, but instead of directly listing out the values, I have a bunch of values given in a table. But in all of these cases that we're going to look at, we have these generic functions that are just made up of f and g, where all I'm told is that f and g are differentiable, so I can find their derivatives. That means that f prime and g prime do exist, so I can use those. And then I'm asked to find specifically, in this case, a prime of 3. So let's look at 15. In 15, it says a equals f plus 2 times g, and we want to find a prime of 3. So in general here, I can think about this as, a of x equals f of x plus 2 times g of x. Sometimes I think it's helpful to have that input in there to begin with. And although it wasn't written out that way, it's implied in the question there. So when I go to find a prime of x, since I have to find a general derivative first before I find a prime of 3, well, let's do these derivatives term by term. Since I'm adding these, I don't need a product rule, quotient rule, or chain rule. I can find them each on their own. So the derivative of f of x is going to just be f prime of x plus derivative of 2 times g of x. Well, the 2 just goes along for the ride since it's a scalar or coefficient, so I get 2 times g prime of x. Now from here, they're specifically asking for a prime of 3, so if I plug in 3 for x, I've got to plug in 3 for all of the x's over here, and I'm looking at f prime of 3 plus 2 times g prime of 3. Well, in this case, I can't leave my answer like this. Although it's equal to a prime of 3, I need an answer that's numeric. That's where the table is going to come into play. So I can find f prime of 3 from the table. I'll go to the f prime column, and then I'll go down to where x equals 3, and that's telling me that f prime of 3 is going to be equal to 4. So the entire f prime of 3 is getting replaced by the 4, since that's what f prime of 3 equals, plus 2 times g prime of 3. Well, I can go to the g prime column, and at 3, I'm getting negative 1. And I know we can simplify those down, but I'm going to just leave them unsimplified for this video. Let's look at our next one. So in our next one, we have b equals f times g. And again, remember, this is the same thing as b of x equaling f of x times g of x. To find our derivative here, I'm going to need to use the product rule. So the derivative, since I have f times g, I'll start with the derivative of the first term, which will be f prime of x, keep the second one the same, so times g of x, plus keep the first guy the same, times the derivative of the second one, which will be g prime of x. From here, we're trying to find specifically b prime of 0, so I can sub in 0 for all of those x's, and we'll get f prime of 0 times g of 0 plus f of 0 times g prime of 0. And all of those values we can also find in the table. I'm going to have you guys pause the video here and find all of those 4 values from that table, and then we'll check it together. So f prime of 0, if I go to f prime and I'm looking at 0, that would be equal to 1. G of 0 is going to be equal to 5, plus f of 0 will be 2, times g prime of 0 will be negative 4. I could simplify it down, but I'm going to just leave that unsimplified. So you can see how these concepts of our product and eventually our quotient and chain rule are being expanded into just generic functions here. And I do want to point out that a calculator can't help us with this, because a calculator can only work if I know what f and g are equal to, because I don't have specific functions. This is where all of those kind of theoretical versions of the derivatives are coming into play. So let's look at 17. We have c equals 3 times f times g minus 4 times g. Again, if you want to rewrite it out, this would be c of x would be 3 times f of x times g of x minus 4 times g of x. Now, the 3 and the 4 would not get an of x because those are just coefficients on here. Why don't you guys pause the video and find your derivative of c of x, and be careful to think about any rules that you might need to be applying. So for here, to take my derivative of 3 times f of x, or 3 times f of x times g of x, I do have to use a product rule. So I'm going to group the 3 with the f of x. So I'll get the derivative of that will be 3 times f prime of x, keep the g of x the same, plus keep the 3f of x the same, times the derivative of g, which will be g prime of x. So there's our product rule for the first term here, minus, now the derivative of 4g of x is just going to be 4 times g prime of x then. If you left the 3 out in front, you would have 3, and then you'd have parentheses around these first two terms, which you could also distribute the 3 in and get the equivalent expression to what I have written down. They asked us for c prime of 1, so we're going to go ahead and substitute in 1 and get 3 times f prime of 1, g of 1, plus 3 times f of 1, g prime of 1, minus 4 times g prime of 1. Why don't you guys find all those values that you need in the table, and then we will check it together. So the first one, I still have that 3. F prime of 1 is going to be equal to 2. G of 1 is going to be equal to 3. Then I have plus that 3 again. F of 1 is going to be equal to 3 as well. G prime of 1 is negative 3. There we go. And then I have minus 4 times g prime of 1 is that negative 3. So there is our whole long answer, and we could simplify it down if we wanted to. But I'm going to have us leave that. Okay, last example. I know this has been quite a long video. There's a lot of concepts in here, but there's also a lot of good examples that you guys are getting practice with. So in example 18, we have d equals g over 4 times f. Again, let's rewrite that as d of x equals g of x over 4 times f of x. And we want to find d prime of 2. Why don't you guys pause the video and find your derivative in general, making sure to use any rules that are necessary. So for this one, we are going to have to use a quotient rule. So I'll have the bottom function, which is 4 times f of x, f of x, there we go, times the derivative of the top, which would be g prime of x, minus the top function times the derivative of the bottom, which is 4 times f prime of x. Remember that 4 is a coefficient, so it goes along for the ride. It is not a constant since it's multiplied instead of added, all over the denominator, which is 4 times f of x. That entire thing is squared, which means the 4 gets squared as well. Here we are going to need a little bit more space. They're asking us for d prime of 2. So if we plug in 2 for all of these x's, we get 4 times f of 2, g prime of 2, minus g of 2, 4 times f prime of 2, all over 4 times f of 2, that entire thing squared. Why don't you guys find those values from the table, then we'll check them together. Okay, so we have the 4, f of 2 is going to be equal to 5, then g prime of 2 is equal to negative 2, minus g of 2 is equal to 2, times that 4, times f prime of 2 is equal to 3, all over 4 times f of 2, which was that 5, and that whole thing is squared. And that right there is our entire final answer. And we can see, especially when we got some product rules and some quotient rules in there, these become much more cumbersome. There is another page in your course reader in this section on page 59. We're going to start class tomorrow together with that, and those are going to involve some chain rules. So in 15 through 18, we did not see any chain rules in here. The reason that is because all of these were just f of x and g of x. So technically, we should have been multiplying times 1 each time, since the derivative of the inside there is 1. But once that x changes, which it's going to on our next page in our notes, we're going to have to worry about the chain rule specifically.